Hello, welcome back. Today we're making a bunch of tapered gibs. For those who do not know, tapered gibs are used to adjust dovetail slides or boxways. They are tapered in lengthwise, a very shallow taper, and the mating surface on the machine tool is also tapered, so the farther you move it in, the narrower the way gets, or the tighter the way gets. And they are kind of tricky to make, but because once you cut the taper, they're a bit annoying to hold on. And over the time I made a bunch of tapered gibs for myself or for customer parts. I want to show you my progress process that I came up with that works for me. These will be made out of gray cast iron, and they are for a 6's 101 watchmaker's mill. I have some rough band-sawed blanks that I'm currently just squaring up here in the mill, and later we're going to cut the taper, and we'll show you my method how to cut the taper relatively easy and to grind it. And we have to bevel it so it fits into the dovetail slide these go in. As you can see, I have my double vise palate held in my larger vise on the milling machine. The older I get, the lazier I get, and if I need two vices on the mill, I throw the thing here on. This is really cool if you need to hold longer parts, or longer parts at an angle, which is nice when you cut taper. So I'm holding these band-sawed blanks are cut out of a 30 by 30 millimeter bar and are band sawed on all sides, so nothing is square, nothing is flat at all. And holding it in two vices at once is nice for this. If the part has a long taper, because it's band sawed freehand, you cannot hold it very securely in a regular vise. There are tricks that you can do. You can put a piece of welding wire or a ball bearing with flat on one side and create some kind of a three-point contact. That works quite well, but can be iffy if you have to remove material in a reasonable amount. But with two vices, even if the part is shaped like a slice of pizza, like a serious triangle, you can hold it with two vices, not a problem. The vices will hit only on one spot with the movable jaw, but you get the two fixed jaws where the part will rest up against, and the two movable jaws that will hit probably on an edge. And that gives you at least 4 points of contact to hold the part. That's relatively secure. I just throw the rough sawn blank in and I clamp it in a way that doesn't bend it too much. You feel this when you tighten down the screws of the vices, and it feels just like a spring. Then something is wrong. Then I just shift it around a little bit and try again, and at some point you find a good position to tighten it down. Then I just mill one side, flip it around, and I try to get it down on the parallels as good as possible just by pressing it down. I'm not hammering it down, otherwise you will torque it and create a elongated potato chip, and you don't want that. So mill two sides kind of parallel-ish. You could also mill one side and surface grind the other parallel. And once you milled both sides, you can stand it upright and square the other edges. All this helps in the later steps of machining when the blank is already reasonably square. I started to use dust extraction when I cut cast iron, especially gray cast iron, because the dust gets everywhere otherwise. This didn't clean up yet fully. I'm taking another cut. 0.25 millimeters, and then this thing should be parallel enough to clean up the sides. Okay, now we got this rough sawn blank into a nice and parallel strip of material. One side milled, other side milled too. And if we check it with a straight edge, it's reasonably straight. This cast iron here was stress relieved. That means you put it in a heat treat oven and cycle it up to, I think, about 600 degrees C, 666, and then let it cool down very slowly. And that should get rid of most of the stresses. You cannot fully remove all the stresses in material usually. You have always residual stresses. Even the mythical 100-year-old cast iron that was stored outside, carried by nude virgins, will still have stresses in it. It might have less stresses, but still stress. Now we clean up the edges. This is a good way to create some nice squarish bars out of really ugly sawn stock. I'm setting up the 2-vise palette to rough mill the taper of the gibs. I still have the palette held in the vise, and I have a screw jack here with a steel ball bearing up here that rests in one of the M6 threaded holes here, so it cannot really move. So it's just in here. And this will allow me to tilt this whole palette very defined and very precisely. Then I calculated the correct gauge block stack up for the angle of the gib needed. Put my small sine bar on here. In this case, a longer sine bar really would be nice. But I do not only have this 50mm one here. Definitely need to make a larger one. And I'm running an indicator along the top. And I'm adjusting over here on the screw jack until this whole palette is at the perfect angle that the sine bar is at. And as you can see, I got it indicated pretty good. This is a 10 micron indicator, reading 0 end to end. We're only rough milling the gibs. We'll grind the final taper later. Okay, cut the taper down to thickness, and I'm going to show you how I'm checking this. Because how do you measure a taper? In this case, my final gib will be 190mm long. That's those two tick marks that I scribed on the ends here. That's 10mm on each side longer than the original gib. The original gib is 170. And that's from here to here. You can see the tick mark here too. And the original drawing from the manufacturer of this machine gives me, over a length of 170mm, a change in thickness of 2mm. It starts out at 6mm here and ends at 4mm here, 170mm apart. And I still have allowance on this for grinding, so this is all not crazy precise right now. I'm measuring with a micrometer the thickness in this area here and over here on the other tick mark, and I do this by having the outer diameter of the micrometer spindle be in line with the tick mark down here. So this is tapered, and as you can see, when I tighten down the micrometer, I can still rack this side to side, and I want it to be contacting on the bottom flat, and I want to measure the thickness at this tick mark. So I have to move over to the edge of the spindle of the micrometer. And that gives me a thickness here. That's 6.3 millimeters. That's my roughing dimension. Final dimension will be 6 millimeters in this spot. The 0.3 are grinding allowance. Now we go over and do the same measurement over here, and we will compare. And we should get 4.3 millimeters out here. Then we know that our taper angle is correct and matching our drawing. And I'm checking the thickness again with the left side of the micrometer spindle to the fat side of the taper. And we get 4.29, which is 10 microns less than it should be. But 10 microns over this length of taper for milling is already pretty darn good. I will do a sketch how this measurement works, because I think it's hard to get the idea in real life. So this is our extremely steep taper that we want to check the thickness in the spot in this cross section. Call it X. We just went ahead and we put a micrometer on here like this. We wouldn't get X, we would get this thickness here. Let's call it X2, which would be more than X, because we're measuring on the edge of the micrometer anvil, and that's farther over here. So we're getting a wrong reading. What we do, we move over and measure in this spot here. And now we get this dimension here, X. This is what we want. So you're measuring on the edges of the anvils, and this is not very precise. But it's still better than nothing. You get a rough idea of what you're measuring, and you can compare, and it helps. So I hope I didn't confuse anybody too much with my sketching. This is a bit hard to explain. Tapers in general are a bit annoying. Got all the tapers or wedges milled. Now I want to grind them. I do not have a sine magnet that is that long. In fact, I do not have a sine magnet at all. So what I came up with is I'm taking 2 of these precision ground magnets here, and I'm super gluing them to this parallel, and I use this as an adjustable magnet on an angled surface. It's a bit annoying because it's a permanent magnet that cannot be turned off, so I have to find a way to get the part off once I'm done grinding. Wiping everything down with acetone and using some rubber reinforced super glue, which is very similar to Loctite 380 Black Max. We don't need a whole lot of it. I'm leaving a little bit on the end so I can get in a small pry bar and lift the part off once I'm done grinding. Squirm it in place. Press it down a little bit. First one done. Those two this is not a matched pair, so I will have to grind it once I stuck them down. Normally with this reinforced super glue, it sticks really well. That shouldn't be a problem strength-wise. I'm also leaving a small gap between the magnets so I can get a small pry bar in there if I need to. Now I have a stinking strong permanent magnet. I'm not sure if this is a good idea. These really are strong magnets. I made a video where I show how to make a very similar version. These are commercial ones. They are crazy expensive. They are about $300 a piece. They show up on eBay from time to time for a tenth of that, so that's a good way to get them, or you make them yourself. So now we'll wait until the super glue has fully cured, and then I will grind it parallel to the parallel. Makes sense. And then I'm going to set it up at an angle. Drop the gib on it and grind it. Okay, that's the setup on the machine. Got the parallel with the two magnets stuck on it. You saw me previously grinding it parallel, so both magnets are at the same height. And then I set the magnet here in this vise on an angle using a sine bar, as before on the milling machine. And I put two small screw jacks out here on the ends to support it, so I do not get any chatter issues. And as you can see, I have a gib up here, and I already ground it. And this seems to work quite well. So far I don't see any major problems. So now as we have ground all the tapers like this, last step, or one of the last steps, is to cut those beveled surfaces here. These are on both sides of the gib, and those allow to slide the gib into the dovetail between the two mating surfaces. These are just clearance surfaces, but they need to be there. And in the past, I tried to cut them with a D-bit that was ground to 50 degrees. That worked kinda, but it's a lot of material to remove that way. I tried surface grinding, which takes fairly long on my grinder, because I cannot remove that much material in a short amount of time on my machine. So now I'm trying something new. I'm face milling them, or with a small end mill, with a carbide end mill. I'm holding it at 50 degree like this, and I just bust the material off of an end mill. It could be as easy. The problem with work holding is, of course, it is tapered, so you cannot just hold it in a regular vise. But I found a very good solution for this problem. Let's bring the camera around. Angle table on the mill, and I clamped a parallel to x-axis onto the table. This is 10mm high, so it's not as high as a gib. And the table is at 50 degree. And the trick now is to take the gib and drop it onto the parallel like this. Take a second parallel, drop it in front of it. Preferable one with a little bit of cross section in height, because it's stiffer. And then we take two big old clamps. And clamp them together. And for good measure, we add a toolmaker's clamp in the center that pulls it a little bit to the table, so it doesn't squirm away in this direction for some reason. So now we tighten them all down. And this is, I did already one, and this is a serious solid setup. It's held basically like in a vise, only that the jaw is much out of parallel and the jaw is 200mm wide. Those clamps can exceed a lot of force. It's crazy. You can get about 10 kilonewtons out of one of these. That's like 1 metric ton. I know. One is a force, one is a weight, but 10 kilonewtons equals on Earth about a metric ton. 981 kilograms. Yeah, now we just face mill this away using the shop vac here to collect most of the chips, or at least a fraction of the chips. And there we go. That's a serious, elegant solution, and I'm quite happy that I came up with this, because all the other solutions I tried so far were quite obnoxious. Once again, there is a reason why I like to have a few large parallels. Make them, steal them, buy them, whatever, but get you some, at least a pair of 200mm and 300mm long parallels. You will use them all the time. Please don't steal. As you can see, I flipped the setup around for two reasons. First, I flipped the whole table here 180 degrees so I see a little bit more. And also, after I milled all the bevels on the first side of the gibs, which was on this side of the parallel, on the other side turned 180. This is now really getting confusing. I took the strap clamps, which were here, and I put them over here, and now I'm resting the gib to mill the bevel on the other side up against this face, and there is a reason for that. If I can get this toolmaker clamp here loose. There's the solution written. Auflagefläche. That's my reference surface for milling the first bevel. This is the reference surface to mill the bevel on both sides. So I was up here resting against this face of the parallel, milling this bevel. And then I turned it around, still keeping my reference surface here. And now the reference surface rests against the parallel from this side. And I cut the bevel on this side. That way, both of the bevels reference off the surface here. If you switch the surfaces here to here, side to side, you end up with very weird geometry, and you don't want that. Okay, it might not be completely clear what I was trying to say there in the shop. We're in CAD here, and you're looking at two gibs. One correct one, the left one, and a wrong one, the right one. At the first glance, both look perfectly fine, and basically they are, but the wrong one, the right one, has a little mistake in it which doesn't make it perfect. Let's say it that way. And the problem is, when we take a look at the face of the gibs, like this, you can see that the left gib, which is the correct one, has a taper angle which you can see from here to here. That's this bevel here. That's this face that's highlighted right now. That's the taper angle. If I tilt the view a little bit, this is the tapered face. This defines the taper angle of the gib. And then we have those two bevels here, which are parallel to each other and are defined against this face here. So it's this angle and this angle here. So that's correct. No compound angles, just a straight wedge with two bevels on it. If we go to the wrong one, there's a lot more going on. We have, again, this here is the gib angle, the taper angle of the gib. This face here. We have one bevel up here, which is correct, because it references off this side here, like this. But we have this weird facet down here, which the other gib on the left does not have. And that happened because this bevel was referenced off this side here. this. So two opposing large faces were used to reference one bevel, and this results in this weird double tapering gib, which basically works because the gib angle still is correct, but it allows the gib to squirm around a little bit more than I would be comfortable with, and it's just not right. It's not the correct way to do it. And also you're losing bearing surface because due to the tapering nature of this bevel, this face here also tapers. It narrows down over its whole length. So don't do this here. The gibs are basically finished. I drilled the oil passage that goes from the fixed side to the moving side of the gib and transfers the oil through. And now I'm milling the oil grooves. I'm using an oil groove cutter. I will talk about the shape of an oil groove later. The gib is clamped to this aluminum subplate here, which is tilted at the angle of the gib, so the top surface here is flat, and I'm indicating, when I run an indicator along here, it's basically very close end to end. I have a 5-degree angle block here because I want a zigzag oil groove. The original design of sixes has straight oil lines. A lot of Swiss machines have straight oil lines like the Schaublins. That's not the most ideal of oil grooves. If you have a linear oil groove, you will end up with a linear wear ridge on your mating surface. That's annoying to scrape out if you rebuild a machine. So we're going for an angled, for a zigzag shape. This is also what in common engineering practice books is recommended. Using oil groove cutter, and I'm just doing a two-step zigzag pattern. Right now I'm cutting the angled, and I'm putting it on parallel to the x-axis, and I'm cutting the connecting lines. This is just, I just laid it out with layout lines. The back side of the gibs, where the oil passage passes through, also needs a lengthwise slot, because when you adjust the tapered gib, it of course moves axially, and it still has to. If the oil port in the fixed part of the dovetail is in a fixed position, which it is, and you move the gib in or out, you still want your oil passage to connect through the gib to your zigzag line over here. So that's the reason why you put this elongated slot here. And that's relatively easy in this case because the subplate here is still set at my taper angle. Then I clamp it with two of these clamps again with brass shim. Butt it up against the fixed jaw of the vise. There we go. That's the connecting oil passage here. That's one of the 3 gibs that I made. Oil passage on the back with the connecting slot. Oil groove zigzag style. Tapered with the 250mm bevels. The ends are oval length. I just squared them up on the belt grinder and deburred it. Also rolled over these edges, radiused them, and they're ready for shipping. A quick word about oil grooves. Let's do some drawing. If you have an oil groove, this is your sliding part. It has an oil groove here, and you have a mating part that it's sliding up against, and you have oil in here. Oil. These two sharp edges of the oil groove will wipe off the oil when the mating part moves over it. So you will not end up with an oil film, with a good oil film here. If, on the other hand, your oil groove looks like this. There's your mating part, and now you have a nice lead-in radius here, and if you have oil in here and the mating part moves, it tends to drag the oil into the between the two parts. And then you have a very good oil film, and wear properties and fretting and galling of the ways can be reduced. So there are different ways to do this. You can use a ball end mill to cut. You can use a ball end mill to cut just a groove like this. Then you take a hand file, a riffler file, or a scraper, and you break this top edge. Put at least a chamfer on it. If you can, put a radius on it. What also works, you can take a large high-speed steel blank, a round high-speed steel blank, or a carbide blank, and use it like a scraper. Take the round carbide blank and push it along your milled oil groove, and that will put kind of a chamfer, a radius in the wrong direction on top of the oil groove. It's better than nothing. And if you want to do really good, you can use Kratex or something else in your electric or pneumatic die grinder and really blend those edges over. Don't go completely crazy. Leave some bearing surface left, but blend those corners a little bit. It will help. Another option is to get an oil groove cutter like this. This is a carbide 2-flute oil groove cutter. As you can see, it has a radius here and a lead-in radius here, and that's the transition radius to your bearing surface. I think these are available commercially, or you can have them ground by a tool cutter grinder shop. There are even proper standards on the sizing of oil grooves. You have to look them up. So I hope you enjoyed this excursus into tapered gibs. I didn't go into excruciating detail, but I think you get the idea how to machine a gib. It's relatively easy if you have a reference, an old worn gib to work off. Then it helps a lot. These are now only ground. If you want to do a really good job, you need to scrape them in. You have to put them in between the two slides, check your end play on both sides of the slide, and adjust the taper angle by scraping very tiny amounts. The owner of these will hand fit them himself, or I might help him. That's to be shown. So I hope you found a little bit something interesting in this video. Thank you for watching, and see you next time.